happy for a minute. Until I get that. So chapter 4 is about integration. Integration is, as we will learn eventually in 4.4, I think, or 4.3. Well, in 4.1 we'll learn integration is the opposite of differentiation. Okay, so this is the thing, this is the operation that's going to undo derivatives. So kind of the way the class goes is we start this whole new process of integration, and we do it for 5 sections in chapter 4. And then in chapter 5 we talk about exponential and log functions, inverse trig functions. So all this stuff we kind of swept under the rug, all the more difficult functions to deal with. We go in chapter 5 and learn how to take the derivatives and integral steps. But in chapter 4 we learn about this new operation called integration. Sort of the way it breaks down. For 4.1 we talk about the basic rules of integration. For 4.2 we talk about area. It turns out that integration actually measures an area, so we need to talk about area under a curve for a bit. 4.3 is about Riemann sums. But Riemann sums are kind of the formal definition of integration. We're gonna cover this lightly. This is too intense for me. So we'll talk a little bit about that, but for the most part, we're going to focus on more simple area problems. 4.4 relates the area and integration. It relates these two things by the fundamental theorem of calculus. Fundamental theorem of calculus says basically if you want to find the area under a certain curve, that process is the opposite of taking a derivative. It is not necessarily intuitive. Finding this area is the opposite of taking a derivative. We'll get there. And then 4.5 is about something called U substitution, which is a special integration technique. Kind of like the chain rule. So this is our task. Calculus 2 goes in and does pretty much all of Calculus 2, at least the first half of Calculus 2 is applications of integration. So if you're going on to Calc 2, you will see this again and again and again and again and again. But we just kind of started up here, right? We touch upon it. This is probably the most important thing if you're going on. Okay, so we'll try to spend a lot of time to make sure you got that down. This is like the chain rule, so just as it's the opposite of the chain rule, so it's just as important. You can't do U substitution, you don't belong in Calc 2. So we'll spend a lot of time. I'll try to bang in here. But we gotta get the basic rules down first. So we'll talk about 4.1 today. So 4.1 is about basic rules of integration. It's also about antiderivatives. Antiderivative is, just like it sounds like, the opposite of a derivative. An integral is yet to be defined. Let me give you kind of a basic motivating example here to teach you thinking. So find a function capital F, we'll call it, such that the derivative of capital F is equal to lowercase f. So I'm going to give you lowercase f. Here you go. Lowercase f of x is equal to 2. And what I'm asking you to find is another function, capital F, such that when you take the derivative, you get little f. So what can you take the derivative of to get 2?
2x.
See? I told you you were going to like this. Right? Because you can check it, right? I mean, because big F prime is equal to 2, so these match. This is called an antiderivative of this function. Capital F is an antiderivative of lowercase f. Antiderivative. Because we basically undid the differentiation. Right? F prime is 2. If you undo that differentiation, you end up back at 2x. Is this the only antiderivative? Is this the only capital F function?
No.
No. Give me another.
Plus 2 plus 3.
2x plus 1 also works. Right? Because if you do the derivative of 2x plus 1, you get 2. Really, 2x plus any constant. So what's going to happen when we define what an integral is, you're going to start seeing a lot of plus c's. Okay, and what plus c's stand for is plus any constant. And the reason we put plus c in is because no matter which constant you add to this, the derivative is still going to be the same. But if I just want a single antiderivative, just any antiderivative, either of these will do. What if I made it a little more? If I made it a little more complicated and threw in, I don't know, just made it x. It's not that much more complicated. It's a little.
X squared over 2.
So now I have to think of what I can derive to get x. Right? So certainly x squared is a good idea. Because I'm kind of trying to reverse my power rule. I'm thinking, okay, I'm going to take the derivative of this, so the 2 is going to come down, and it has to equal this. Right? But if this 2 comes down, I'm going to get 2x, not x. So this is close, but not quite right. I can fix it up by putting a constant out front. So if I put a constant of 1/2 out front, then when I do the derivative, the 2 comes down, and these cancel, and you're left with just x. Yeah, there's a general rule. Right? Just like there's a power rule for differentiation, there's a power rule for anti-differentiation. Right? So in complete generality, if I gave you, well, let's not do complete generality first. What if I gave you x to the 5th? What's the antiderivative? Or what's an antiderivative? Is it just... Right, so it's not just x to the 6th, because the 6 would come down and that would screw you up. But if you put a 1/6 out front, then the 6 comes down and cancels. And now this will equal x to the 5th when you do the derivative. So that can give you a general rule like this. What if your function that you want to get as your derivative is x to the n? So for any number n, what would the antiderivative be? Or an antiderivative?
1 over nx.
1 over n.
Yeah, so you're going to need, look at the pattern, right? You have one more on the power, and then you divide by that power. So it'll be x to the n plus 1 over n plus 1. You can either put it over n plus 1, or if you keep it in this pattern, it would be 1 over n plus 1 times x to the n plus 1. So if I put, what do you think happens if I put some numbers? So make it some constants. 4x cubed minus 3x squared. Give me an antiderivative here.
4x to the fourth divided by 4 minus 3x to the third divided by 3.
So just like with differentiation, when you do anti-differentiation, when you go backward, you can split it up across a minus sign. So you can do the antiderivative here, and then you can do the antiderivative here. And just like with differentiation, if it's a constant multiple, you can just let it fall down. So the 4 will come down, and then the x cubed becomes x to the fourth over 4. So the constant multiples can follow, but then the x part has to be anti-derived. You have to do the opposite of differentiation, which is this one. And then you go on. The minus 3 will follow, but then you'll add 1 to the power and divide by the result. So capital F of x, the antiderivative, or an antiderivative here, will just be x to the fourth minus x cubed. What if you didn't believe me? What if you thought I was lying to you, making this stuff up?
Just take.
You could check, right? You could check by just taking the derivative, which isn't a lot of mental work, I hope, right? X to the fourth becomes 4x cubed when you do the derivative. Check. Right? Minus 3x squared. Check. Okay, good. Good. Oh, did I do D twice? That D was unscheduled. That was an unscheduled stop. What about, all right, so let's make this harder. Ooh, let's do cos x first. Oh, I guess I should have done sin x first, so I'll do cos x. So, you have to come up with a function, oops, capital F, that when you take the derivative, you get cosine. Sine. It's gotta be, right? Some kind of sine. You want to make sure the sign's checked, right? I mean the SIGN. Meaning if you take the derivative of sine, do you get back here? Is the derivative of sine positive cosine?
Yes.
Yes. So this checks out. What about if I give you negative sine x? So what do you take the derivative of, right? That's what this is asking. What do you take the derivative of to get negative sine? Cosine. Right? Because the derivative of cosine is exactly negative sine. So this is an antiderivative. Just trying to build you up. Negative cosine. Yeah, so you got to be careful though. Right, if I don't put the negative sign in here, and I just want an antiderivative for sine x, for positive sine x, will positive cosine x work?
No.
No, because if you take the derivative of positive cosine x, you get negative sine, which is bad. So you have to fix it up by putting a negative out front. Because the derivative of cosine will give you negative sine, but then this negative will cancel. Check it. F prime of x will equal, the negative follows down, but when you derive cosine, you get negative sine. So the negatives cancel to a positive, and you're back to what you want. So it does check. So I guess hopefully you're getting the idea. Ooh, although. Come on, marker. Come on. if I gave you something like square root of x? So again, the question is, what function do I take the derivative of to get square root of x, right? So how do I go backward? How do I take the antiderivative of square root of x? What do you do for the derivative? Right, but you have to change it to a power first, right? So it's the same idea for going backward. Change this to a power first. And then the power rule for anti-differentiation is going to apply. Right? When you go backward, the opposite of a derivative, you add 1 to the power and then divide by the result. So the antiderivative will be x to the 3 halves, because you add 1,
over 3 halves.
over 3 halves, right? You divide by the same power. Which is kind of funny to write, because you have a fraction in the denominator.
2/3 times.
So I'd probably flip it up to 2/3. So J, let's see. Let's do x plus 3x squared over cube root x. So I want the antiderivative. I want a function, when I take the derivative, I get this guy back. Is there an anti-quotient rule? Why does it not surprise me that you guys want an anti-quotient rule? I don't know an anti-quotient rule.
6/3 minus 1/3.
Yeah, so why don't we go ahead and split this up, right? Because you can divide the cube root, well, you can change the cube root to a power and then divide it into both of them. So you can do some algebra here to make it a little more workable. Right, so change this into x to the 1/3, and then split the division among both of the top terms. And what happens when you divide like bases? What do you do with the exponents? Subtract. So x to the 1 over x to the 1/3, subtract the exponents. X to the eyes out to the top. X to the 2/3 plus 3x to the, looks like 5/3. Right, because this is 6/3, 6/3 minus 1/3, 5/3. That's just the algebra. I haven't actually done the calculus yet. So now I do the antiderivative, which says add 1 to the power and divide by the result. So if you add 1 to 2/3, you add 3/3, so it becomes 5/3 over 5/3 plus 3x to the 8/3, because you add 1 to the power, over 8/3. I'd probably flip them up. It's a lot prettier that way. So 3/5 x to the 5/3 plus, then when you flip up the 8/3 is 3/8, it'll become 9/8 x to the 8/3. So, I don't know. If you so far?
Mm-hmm.
So, the new term for this process, or at least a similar process to this, is called the indefinite integral. So the indefinite integral of a function is the family of all possible antiderivatives. So the indefinite integral is actually a family, it represents a family of functions, it's not just a single function. And it's the family of all possible antiderivatives. So an integral, the indefinite integral, is an antiderivative, but it's not just one, it's all of them combined. So and let me give you the notation and then we'll do some examples. What you're going to start to see is this elongated S, okay, which is an integral sign, or an integral symbol. And then inside of the integral symbol, or next to the integral symbol, you'll see the function that you're supposed to take the integral of. And then you'll see a dx, or some sort of d something. This is just like the dx that you see in dy dx. It's meant to represent an infinitesimally small change in x. But for the most part, you're going to use it to tell you what variable, this is like what you integrate with respect to. Kind of like how we were doing d dt sometimes. If it's a dx, you integrate with respect to x. If it's a dt, you integrate with respect to t. This tells you the variable to integrate with respect to. You really can't have this symbol without this symbol. Okay, so these are kind of a pair. Right, these always show up together. And then this in the middle is what we're actually interested in finding a family of antiderivatives of. This is the function we want to integrate. So this, when you see this integral of f of x dx, or the integral of f is how this is written, read, you want to find an antiderivative, any one, but be careful, the integral, the indefinite integral of a function is not just an antiderivative. It's the family of all possible antiderivatives. So what you do to show all possible antiderivatives is you put plus. So any antiderivative plus a constant will give you all possible antiderivatives, or all possible, antiderivatives. So that will give you the family. So kind of, I don't want to belabor this too much, but if I want you, a quick sort of picture here, if I want you to find the integral of 2x dx, what would this be?
X squared plus c.
Right, so the integral is an antiderivative plus a constant. So the antiderivative, or an antiderivative says you do your power rule, leave the 2 alone, but then add 1 to the power and divide by it. But since it's an indefinite integral, you add a constant. So after simplification, you get this. So this was, your original function was 2x, right, which is just a line. But then your indefinite integral was actually a family of functions. So you get a different function every time you plug in a different c. So x squared plus c, well, here's one possible antiderivative. Here's x squared. And what the relationship between these two is if I take the slope at any point here, it's equal to the y value. Right? So like if I found the slope of the tangent line here, it would be at x equals 2, it would be equal to the y value of x equals 2.
But it doesn't matter if you move the function up and down.
Right. So this is one possible antiderivative. The indefinite integral says, you know what? I want all of them. I want all possible functions that have this as their slope. So you can move it up, or you can move it down. As long as it's a parabola, they're all going to have the same formula for their slope.
Will those get wider?
Well, that's because
I know, that's not the drawing.
But but they're also, you know, they're all, this guy would be x squared plus 1, this guy would be x squared plus 2, this guy would be x squared minus 1, x squared minus 2. So this formula means all of these, all possible constants being added to x squared. So it's actually, you want to think of the indefinite integral as a family of functions, not just a single function. Basic integration rules. You can memorize these. Hopefully most of them are intuitive. But when you do the indefinite integral, so I'm going to list a bunch of indefinite integrals. Remember, an indefinite integral is just like an antiderivative, except it's all possible antiderivatives. So what is the antiderivative of 0? Or antiderivative? So what do you take the derivative of to get 0? Any constant. All right, so then what is the antiderivative of a constant? Yeah, so what do you take the derivative of to get just a constant? X times that constant. That's an antiderivative. What's the indefinite integral?
Plus c.
So that's the family of functions whose derivative is the constant k. And this one we just talked about. If I want the integral, the indefinite integral of x to the n with respect to x, what's the formula? X to the n plus 1 over
n plus 1.
plus c, because of the integral sign.
About minus 1. N equals, that's sort of stuff's on the book about n can't equal -1.
Yeah, well, what happens if n equals -1 here? Divide by 0. Doesn't make any sense. So it turns out for n equal to -1, there's a special formula, but we don't learn until chapter 5. Because you need natural log. So this is only valid if n is not equal to -1, but if you try to use it with n equal to -1, you're going to get garbage anyway, so it's not a huge deal. If you take the integral of a constant times a function with respect to x. So this rule is kind of like the same rule we have in derivatives. If you have a constant multiple, it just follows along. And the way it looks for integration is you can actually pull it out of the integral. So if you have a constant times a function and you want to do the antiderivative, or I guess the indefinite integral, the constant just follows along, and then you do the integral of the function. Do I need to put plus c here? No, because I haven't actually done this integral yet. Right? This says the family. When I actually do the integral, see, none of these have integral signs anymore. That's why there's a plus c. But this still has the integral sign, so you don't need a plus c. Oops. So what do you think happens if I take the integral of the sum of two functions? Or differences? Yeah, so the integral of the sum you can do by just taking the integral of the first plus the integral of the second. Just like with derivatives, the same thing is true for subtraction. Right? This can be plus or minus, and then this will be plus or minus. But you do not have a rule like this for multiplication or division. Right? If you have a multiplication inside, you have to simplify that first before you can do the integral. Addition or subtraction, you can just take the integral of each. But multiplication or division, you have to simplify somehow first. Oh, and then we have all of these. Well, let's do cosine. Oh. So we know all of these indefinite intervals. So cosine. What do you take the derivative of to get cosine? Derivative of sine is cosine. So the integral of cosine is sine x plus c. There's your family function. What about cosecant squared? What do you take the derivative of to get cosecant squared? Yeah, so you gotta be careful here. The derivative of cotangent. Oh,
Negative.
the derivative of cotangent is not cosecant squared quite, right? It's negative. Got my pattern wrong. We can fix up the pattern in a second. But this guy needs a negative because originally, if you take the derivative of cotangent, you get negative cosecant squared. But if I want to get positive cosecant squared, I have to put a negative in front. So the integral of cosecant squared is negative cotangent. What about the integral of cosecant cotangent?
Cosecant.
So usually when you take the derivative of cosecant, you get negative cosecant cotangent. So if I want to get positive, I have to put a negative. So the integral of sine, you would think it's, when you do the derivative of cosine, again, you don't get exactly sine. When you do the derivative of cosine, you get negative sine. So we need a negative here. And then, what do you take the derivative of to get secant squared? Tan. And that one's okay, there's no negatives. What do you take the derivative of to get secant tangent? Secant. So I guess I probably should have switched these so that you get all negative answers on one and all positive answers on the other. Sine x dx. Negative cos x. And the integral of cos x. I never remember them like this, but that's a nice pattern, I guess. I just remember the derivatives, and I can do the integral just means you put on the plus. Okay, so example. So these are all these are basically all the integration rules we know right now. So if I ask you to do an integration, if I give you an integral, you're going to have to use one of these. You might need to do simplification first, but then it comes down to one of these. So if I mention this integral, (7x² plus cube root of x dx). Right, so now this is an integral sign, so I know I'm going backward. I'm trying to find the antiderivative and then add a c. Because it's a plus sign, I can do the antiderivative of each one. So this is really, I just need to do the integral of 7x² plus the integral of cube root of x. What do you think I should do with the cube root of x? Make it a power. So then I have to do both of these. Since I just have x to a power, I can use my power rule. Now when you do the power rule, the integral sign goes away. Okay, so as soon as you add 1 to that power, you're actually calculating the antiderivative, so the symbol's going to go away. So it's going to be 7 x to the third over 3 plus c for this integral. What about this guy? Add 1 to the power, so 1/3 plus 1 is 4/3. Over 4/3. Plus another constant. Technically, the way I did it. One thing you want to get used to in integration is when you do two integrals and you add them, these two constants usually are rewritten as a new constant, right? Because C1 plus C2 is just another constant, so we'll call it C. So even if you have 10 integrals and you're adding them together, you're just going to end up with one constant at the end, which represents what you would get if you added all these together. So I'm going to write this final answer here as 7/3 x to the third plus 3/4 x to the 4/3 plus c. Right, so even though I broke it up into two integrals to make mine work a little easier, I still only end up with one constant at the end by combining these into a single. Oh, 4. All right, one more. I'll let you go on here. What about the integral of, what I want to do? Ooh, that's a good one. Sine theta over cosine squared theta theta. So you got to be careful here, right? You might think, well, you can split up the integral and just do the integral of sine and then divide it by the integral of cosine. Does that work? No. You can only split up the integral if it's addition or subtraction. Division and multiplication, you have to simplify first. So I want to somehow make this look like the derivative of something. Yeah, so, yeah, because of the cosine on the bottom, I know I could have a secant in here, right? And I also know I have a sine and a cosine, that might be a tangent. So to actually do this integral, you have to rewrite this guy as sine theta over cos theta times 1 over cos theta. Because that gives you sine over cosine is tangent, 1 over cosine is secant. Yeah. So once I break this up into a tangent and a secant, this guy I recognize. This is the derivative of something. What is this the derivative of? Secant x.
Secant theta.
Oh, secant theta. Oh, okay. This is the derivative of secant theta. So my integral is going to be secant theta, right? Antiderivative plus a constant. Right, so I can't split this up at the beginning. I can't split this division up. I need to somehow manipulate it to make it look like something I know I recognize. All right, I'm out of time. I'm all done. I'll do a little bit of review of this on Wednesday.